Welcome to Datadog Illuminated. Serverless can save you money, but the trade-off is that it's weird. Your CPU gets frozen between requests, you have extremely limited resources, and every millisecond of initialization time costs money. So these constraints can make observability hard, and running the Datadog's agent in this environment was less than ideal. The agent was designed for long-running servers with generous resources, not the tiny ephemeral sandboxes that Lambda provides. So AJ Stuyvenberg and Datadog's serverless team, they did something bold. They rewrote the Datadog agent from scratch. And the results were dramatic. I wanted to understand this journey. Why rewrite instead of refactor? Why Rust when no one on the team had Rust experience? And how dramatic are these dramatic results really? So today's guest, AJ, walks through it all. Let's do this. All right, I'm here with AJ. AJ, will you introduce yourself, please?
Yeah, of course. Hey, everyone. I'm AJ Stuyvenberg. I'm a staff engineer here at Datadog, and I work in the serverless group. Today, I'm really excited to talk through Datadog's journey to rewrite our serverless agent and kind of explain why we did it, the steps we took, and the results we had.
I already have questions just from this part. Let's start by describing the problem space that inspired this journey to even begin.
Datadog has a long history as an observability and telemetry company, so we have this very mature data collection process and set of programs that we deploy to customers' infrastructure that can send data back to Datadog. Maybe 5 or so years ago, we decided we were going to start extending that into new technologies like serverless space, which has been a lot of fun and very interesting because dominant compute platform for the longest time in the serverless space has been AWS Lambda. That was kind of the first serverless technology that kind of landed, I think, in 2014. And it's very unique. And I actually would go so far as to kind of say it's very weird. If you're coming from a traditional background in Kubernetes or bare metal servers or containers or kind of any of these different tools, Lambda is very weird.
There's so much talk of Gen AI agent. So when we say agent, kind of like you said, we mean the Datadog agent. Nothing to do with Gen AI in that case.
Correct.
And then let's talk about Lambda is serverless, right?
Serverless as a definition is really a marketing term, but it's kind of been distilled by the community into a few key behaviors. And the first is you never pay for idle. And the second is it scales to zero. And the third is that auto scales for you. So the whole principle is you write some code, you hand it to the provider, and they are responsible for running it, whether you have no requests in a given day, or you have 10 million, or you have 0 to 10 million in a day and back again. And the principle is you only pay for what you use. But with these principles and these behaviors that we like come a number of trade-offs that we have to manage. And that's where I think this gets really interesting. Okay. So the first big trade-off is in order to make this stuff scale to zero, the cloud provider can't leave your functions and your processes running all the time. So when they think that your function won't receive any more requests, they'll actually freeze the CPU and sort of suspend the process. So the first is between requests, the CPU gets frozen. And this is a really big shift from a modern web application deployed on like Kubernetes or on bare metal, where you can assume that you have a process that kind of runs unencumbered and indefinitely. And when you have to write, especially telemetry collection code, and assuming that is no longer the case, it's a big difference because we end up in the situation where a lot of telemetry code says every 10 seconds, check this file and see if it's grown or see if there's new data or something. And that no longer applies in a serverless environment. The second is that these are very small sandboxes traditionally. So the smallest Lambda function today is about 128 megabytes of RAM. Lambda does not publish how much CPU they give you at that setting. They kind of keep that a little bit of a secret, but they do say that at 1.7 gigabytes of RAM, you get one full vCPU core. So you can imagine, 128 megabytes, you're getting close to like an eighth of a vCPU core or so.
Very small resources. Okay.
And then the next thing is that Lambda is orchestrated as a set of teeny tiny isolated sandboxes that can't talk to each other. This is very different from like a cluster environment, and they're isolated because it allows AWS as a provider to move them around when they need to, shut some down, bring some back without necessarily coordinating. So your code and your serverless, agent code or serverless Datadog agent code has to run assuming it can't talk to other service instances that are in the same function. And that makes it hard to come to a quorum, come to a decision on something. Any of the things like sampling data is a little bit more difficult in a serverless environment.
What I'm hearing is it's objectively weird, objectively a different way to think about computing.
Absolutely. Yeah.
But
and it comes with a lot of benefits, right? Like to get those benefits, they have to make these trade-offs. And that's true for all engineering work.
For literally everything in life ever.
Exactly.
Specifically, though, with Datadog's agent, there are some big issues here.
Yeah. Datadog's agent is a very battle-tested and well-proven piece of technology. It initially, I think 10 years ago, was written in Python. Now it's been written in Go for several years. It's fully designed from the ground up to be deployed on a server or in, a Kubernetes cluster or on a pod. It is designed to run for a very long time, and it has a bunch of assumptions about how data is handled in the process. And that's done for a reason. It's done to operate at scale. It's done to be extremely efficient across dozens or hundreds of nodes of servers. That doesn't necessarily apply to serverless, because instead of having one Datadog agent for hundreds of application processes, you have one Datadog agent per application process. That's how Lambda works.
Yeah, for a very small application process.
Correct. Yeah. And as a result of these design constraints, the Datadog agent is quite large. It's 55 megabytes, and that's the one that we purpose-built for serverless. So we made an initial attempt to repurpose our Datadog agent for serverless. We wrote a number of custom modules for it. We stripped out a lot of code we weren't going to use, and we compiled and kind of got it to the best we could. And it was like around 55 megabytes in size. But that also comes with another painful part, which is cold starts. The cold start penalty for our Go agent in Datadog was about 400 milliseconds of startup time.
Okay.
So because Lambda shuts down your CPU between requests, when you have these scaling events, it needs to bring more compute back up. And when it does that, your customers are waiting because there's no server to serve that request. There's no Lambda process. So that initialization is called a cold start. And that only happens once, and the sandboxes can then be reused for a number of hours. But the longer that time is, the more your customer or your user waits.
That's like end user time right there. Plus,
precisely,
it's compounded by the whatever initialization the customer's function.
Yeah, and there's three components actually to it. The first is Lambda has to boot stuff up itself, right? So if you're running a Node.js function or a Python function, those runtimes, Node or Python, have to start. They actually have to pull that code into the sandbox. It's streamed in. They have to initialize and bootstrap, and then they can start loading our code, and then they'll start loading the customer's code. That is always going to be a serial operation. It doesn't really well to multi-core processors, so it's very much a bottleneck in the process. Yeah. So you want to do everything you can to kind of limit that cold start time.
Because I think 400 milliseconds, I mean, if I had to wait that, would I even notice less than half a second? But then if you add that, what you're saying, pulling in the code plus the customer's initialization plus all of that, it can get
quite high. And customers do notice. One of the most painful things about serverless is because, maybe a little tidbit, when you're deploying serverless functions, you're kind of constantly redeploying them. And when you do that, a new deploy invalidates all of the existing sandboxes. So then you have to have another cold start. So especially developers feel this pain. Even if your customers, for the most part, serverless services running at scale don't run into very many cold starts because Lambda gets very good at predicting when sandboxes should come online or not. But you as a developer feel it intensely because every time you deploy, you get a cold start. So it gets in your mind and you're thinking about it every single time.
It messes with your flow state. Developer time is valuable.
Yeah, exactly. Yeah. It's like compilation time in a serverless environment. Yeah.
I see that AWS Lambda is a special place, and I see that the Datadog agent is clearly not defined for that. But why rewrite as opposed to reconfigure or refactor?
Yeah, we had initially tried that, and we got to the point where we had diminishing marginal returns on what we could reconfigure and what we could do. Go as a runtime had some limitations for us where we couldn't, for example, dynamically load different components. But for example, we were really targeting a big reduction in initialization duration.
Okay.
We also knew that most of that code we didn't need. It was about 20% of the actual agent code base we didn't even need. So there, you reach a point where stripping everything out over and over again is more work than building the purpose-built thing that you need. The second is because we were in a very special environment and the Datadog agent is, a large project with hundreds and hundreds of contributors, we would be, victims of large changes and have to, rebase things or eliminate bugs that were maybe introduced upstream where they're not a bug in the traditional agent, but once you apply them to serverless, that didn't quite work the way it was intended. And that was a challenge, like an impedance mismatch, where the design of the program and the ethos of the program was being violated by us. Like we were taking it in a different direction than it was intended. So it wasn't even wrong. It just was wrong in our context. So we picked Rust, and we picked Rust for a few key reasons. The first and maybe the biggest is that there is no garbage collection in Rust at all. You manually manage your memory. That's a little bit of a daunting task if you're brand new to Rust. If you're coming from the background of a garbage collected language, it can be a little intimidating, but we want to get the best performance we can, the best kind of bang for our buck in this small environment. So
So one reason to switch to Rust is no garbage collection.
Yeah, exactly. The other reason, and kind of maybe the biggest reason specifically for cold start time, is that Rust creates very, very small binaries that use very little memory. So by default, kind of out of the box, the runtime of Rust itself is quite small. It then creates these smaller binaries, and you only pull in the bits you need by default, and you end up with this usually pretty performant, pretty efficient program at the end of the day. That led to fast startup times. So our initial POC was showing something like 50 to 60 milliseconds of initialization time versus the 400 that we were getting with the Go agent.
It's just so interesting. It's just a whole different ballgame. It's exactly. Like crash first design. Like we're designing to with the coming up process as a first class citizen of our program. It's
a type of thing where if you are a traditional application developer, none of these things maybe matter to you. In a serverless environment, they really do. So it's a classic, like this other thing was never designed for that. And it will be very hard to squeeze it into those constraints versus building something with the same ethos that we can go from the ground up. Rust is sort of famously known for memory safety. And I saved this one for last because it's very important in a serverless context. In serverless and in Lambda specifically, not true for other cloud providers. In Lambda, telemetry processes are packaged as something called a Lambda extension.
Okay.
In practice, when you're deploying Lambda extension, if at any point your extension crashes or fails to respond to the runtime orchestration process, Lambda sees this as unhealthy all around, and it just shuts the whole sandbox down, and including the customer code, their server process.
Customer code.
Yeah. So in a traditional server world, something like an agent is just deployed on a sidecar process, or even like an actual Kubernetes sidecar. So it has its own life cycle. It can crash and reboot on its own. It can roll back. It can kind of be segregated and separate from the application process, so you don't have like a negative impact on that. That's just not true. The fates in serverless, the fates of the customer code and the telemetry and the Datadog agent code are intertwined.
That's high stakes. Yeah,
exactly. Now, then you have one benefit, which is like one application process per agent process in Sandbox. So if something goes horribly wrong, hopefully it only affects one request. But it comes at the cost of like, if something does go horribly wrong, it does completely like delete that application process from your fleet of hosts. So it's kind of a scary proposition.
Absolutely. We want to rewrite because it makes the agent lighter. You want a rewritten version that's lighter weight because you only need 20% of the code. That's almost nothing. You want to eliminate those upstream bugs that get introduced very rightfully because you're using it for a different reason. And then you want to switch to Rust for a host of good reason. So is there any other reason that you want to rewrite?
There were a couple things, but we should get there. Let's talk about that maybe in a little bit.
That's suspense. So we have our request, the initialization step, which right now before the rewrite is 400 milliseconds, right? And then we have the customer's code, the function that runs, which in serverless, you instead of saying application, you say function.
You can think of it like application, though. That's exactly, it's the customer's code or whatever you upload to Lambda will execute here.
And then is that it?
No, not quite. So the very first time the sandbox boots up, by default, we'll start sending data back to Datadog, because kind of alluding back to our point about these being isolated sandboxes, when this first starts up, we have no idea how busy this function will be. Maybe it'll get one request for the whole day, So if we wait to send any data until Lambda decides to shut down the sandbox, we could wait 10 minutes and you wouldn't see anything in Datadog for that time. So kind of by default, we try and kind of do that and send some data back to Datadog. So when people go, they see that their function has been executing.
So basically, a customer who wants to include Datadog to process all their telemetry data, to collect and process telemetry data for their serverless, they are adding time at the beginning for initialization, and they're adding time at the end to send
on
requests.
A cold start especially. Now, keep in mind that on subsequent invocations, the initialization process is done, the sandbox is warm, so we can just skip right to the function running, and then we'll send some data back to Datadog. But that is correct, yeah.
So for the rewrite, tell me what one or many challenges were.
Well, I think the biggest challenge that we had was we didn't actually know Rust. We were a small team. There's about 3 of us, 3 to 5, depending on kind of what phase of the project. We knew that we were targeting this for the reasons that we kind of laid out earlier. We knew that this was the right choice, but we didn't have any production experience with Rust. We live in this world of LLMs and generative AI, so we relied on that very heavily, we were able to create very solid acceptance tests to know what like good was and what correct was, which allowed us to have like a high degree of confidence. But yeah, we can, talk through some of the results and kind of explain how we roll this out, I think is maybe the next step.
I love it.
The first needle we needed to move right away was the cold start time. That initialization time needed to change.
Yeah.
And when we first got a proof of concept built and started out, we saw that was about 50 milliseconds. And that was very early in the project when it didn't do all of the things that the rest of the program needed to do to go to production. But we still kept that as like a target limit, and we had that as a monitor in Datadog. So if we ever started to exceed this threshold time of like the additive overhead of this agent, we would have like an alarm go off, and we would go and look at the code and see what was integrated into the branch and what caused this regression. And we found many things throughout the whole process. But I think that was key to holding this bar, is that we monitored it and we kind of dropped everything when this invariant was violated or this rule was violated, so we didn't kind of start exceeding the limits. Because performance engineering is very hard to do when you have some big number and you want to take a step function reduction. Like I said, for the most part, you have to do a whole rewrite, rethink things from the ground up. And as performance regressions slip into the code base, if you're not constantly looking for them, they're very, very hard to unwind and identify in hindsight. So we kept a very close eye here.
That's so smart to keep it like the second it's crossed, then you immediately address it before it like becomes the bedrock for other code that's built on top of it.
Exactly. And then the way we drove that, and a big part of why that's smaller, is the binary size got a lot smaller. So we went from this 55 megabyte binary down to about 7 megabytes. And not all of that is Go's fault. It's not the language specifically. I mean, Go does create large binaries by default, but it was by virtue of the fact that we had been repurposing a lot of other code that we didn't necessarily need. And we went from 55 megabytes to 7 megabytes. That like directly influences the cold start time reduction, because that's just simply much less data that Lambda has to pull into the sandbox and start running during the cold start. So it's just faster.
Did you have to do a lot of thinking or research or anything about what functionality you were pulling?
The kind of key aspect that we did was we rolled these things out with both the Go agent and the Rust agent together. And then we monitored the Go agent to see which configurations we didn't support in Rust. So we would get a little feedback mechanism that would tell us when we didn't, there was some esoteric feature that we didn't realize was being used, that is being used. And then we would put that on our roadmap and then add it for support.
Awesome. What other results did you see?
Yeah, memory reduced by 50%, which is a big win. That like is a direct cost driver for Lambda. So the more memory you use, the more you pay.
So all of these are like pretty huge results. This is impressive.
Yeah, and we had a 2x reduction or improvement in our tail latency in our like P99.9. The tail latency is the stuff on the far edges, either on the short side, on the 0 to n side, or the long side, like 100% and down. And when we talk about percentile metrics or percentile latencies, we generally just say, okay, the whole curve is 100%, and P99 is 99% and up is like that's the P99 time, and then P95 is 95% and up, and a P50 would be like your median latency. Okay. So distributed systems, and especially software systems, tend to have very long tails. It's not like the one you see in your statistics class where it's a short, it's just a very even curve, a normal distribution. In software systems, they have very, very long tails where, and you've probably experienced this if you use Datadog or looked at your own metrics, where most requests may take 40 milliseconds and then all of a sudden one of them takes 2 minutes. That's a very, very long tail. And that is something that we seek to reduce. And the reason we do that is by focusing on your P99, you often improve the median too, because the more you improve the outliers, the more you shift everybody into kind of that middle group and you solve these edge cases. And that's really important, because in a SaaS product, everybody who is hitting your painful edge cases is typically your best customers. Your median customer that's maybe barely using your product or just trying it out is probably not going to have that long tail experience. It's the person with a ton of data doing, sending a lot of metrics or a lot of logs or a lot of spans, or, they're turning on everything in a small environment because they have a performance sensitive application and then they really need Datadog. So your P99 is really your best customer having their worst experience. So we do focus on that quite heavily. Yeah.
I love thinking about it that way, just by sheer numbers, just like heavy use alone. That makes a lot of sense.
And like I alluded to earlier, we had to get this out into production in a safe way, and we didn't want to do a real big, hey, flip the switch and everything's on. So we had this like safe rollout procedure. Because the Rust binary was small enough, we packaged them together, and we had a little bit of code, which would, as I alluded to, it would analyze the configuration of the customer function, and it would figure out if we were missing some feature. If there was some feature that they had used that we didn't yet support in Rust, then we knew that as we went. I think we started with metrics and then logs, and then we added tracing, and then we added, application security and a few other features. That took some time. So when we detected that was the case, we would send a metric back to Datadog, and we would say, okay, we're failing over to the Go version for this reason. And as we collected those reasons, we were able to kind of rank what we needed to accomplish and, implement that. And then we would remove that missing feature from the failover. Then we'd ship a new release, and we'd wait to see what the next thing was.
So the idea wasn't to ship Rust and Go together permanently. It was just like as part of getting it started in the first place. The Go that everyone's already using, you're just going to add the Rust on top of it, which isn't that big of a deal because you got it down to 7 megabytes.
Yeah, correct. And it was even smaller at the time. Like the final release where we included every feature from Go in Rust was 7 megabytes, but even at the time it was like 4 when we first started doing this. So we started the process. We had these dual shipping thing rolled out in under a year, which was fantastic pace for what we were trying to do. And then I think it took another 6 months or so to actually fully remove or delete the Go agent from the release. So then that was finally like fully deprecated, and that got us to the final size of about 7 or 8 megabytes. Yeah.
Amazing. So you rewrote like the core piece of Datadog software for a whole new environment in a language you didn't know in under a year in a way that's provably successful. Yeah. That's really freaking amazing. So here's our before. It says 400. We got down to 50 milliseconds. So that's our init there, which is not really as small as it should be to scale. And then we have the customer code that runs.
We were looking for ways to push down the tail latency even further. And we had already had this, I think we called it a periodic flush strategy in the Go agent, where if the function was busy in the sense that it was being invoked more or less, constantly. So there was enough requests that the sandbox was very busy and it kept running. We would buffer some data. We would batch it. So we would batch a bunch of data over maybe, a minute or so. And then after that, we would flush that data. When we're flushing that data, we were preventing that sandbox from picking up another request. We were blocking.
Okay. Yeah.
And that can be key because occasionally Lambda does not send any more requests to that sandbox and it shuts it down. So you don't know when that's going to happen. But what we were able to figure out is if we... Oh, sorry, go ahead. What's your question?
Are you saying there's a chance this gets truncated too as part of that? Like, not all the data gets sent because of that?
Correct. If you don't signal the Lambda runtime that you're going to block it from receiving a new request or from moving on in the state machine, it can at any point just suspend your CPU.
Okay.
Which is a scary thing. However, we came up with this innovation that we called a continuous flushing strategy. And what it does is it begins sending data to Datadog, but then it also signals to the runtime and says, we're done here. You can shut down the CPU if you need to. Now, we only do that when we know the function is very busy, where we've seen a number of invocations of the sandbox frequently, and we know that it's unlikely to be immediately reaped into the Lambda sandbox environment again. And what that allows us to do is we wrote a bunch of code in the Rust side to keep track of these pending requests. And even as Lambda will freeze the CPU for a little bit of time, as long as it wakes up before on the server side we close that socket connection, that data stream is still valid. That TCP connection to Datadog is still valid, and it can just push bytes whenever it has available CPU. So over the course of many invocations, we can actually flush little slices of data at a time. And that allows us to have almost no tail overhead on the back half of the transaction. And we keep track of all of these. So if there's ever a point where Lambda does freeze the CPU for a few minutes or, an hour or even shuts it down, during the shutdown phase, we're able to completely flush all the data in a blocking way like we were doing previously. But in the steady state, which is, most of the time for busy Lambda functions, this allows us to have almost no overhead at the end of a transaction. And we can just kind of keep sending little bits of data over and over and over again while the next invocation runs.
Am I understanding correctly that you're able to find times in the customer code where the CPU is not being used and then use it to
we
flush?
Don't do that. That's how the Linux scheduler kind of works.
Okay.
So when typically Lambda functions are doing waiting on some amount of IO, right? They're talking to a database, or they're pushing a message to a queue, or they're maybe reading a file from S3. And during that time, that CPU will yield to the scheduler. And then the scheduler would say, oh, well, Datadog's waiting to send some data back. We'll just do some of that right now. And the Linux scheduler is called the completely fair scheduler. It's very mature and it's pretty good at that. So there's typically enough time to do that. And even when there's not, there's just a little bit of slip in Lambda's algorithm between invocations where we actually get a little bit of time where we can flush some data. And we don't need that much. During IO waits, we're flushing a bunch of data. And the only way this works is we have to really keep an eye on these requests, right? We have to make sure that they have completed and that they're successful. And if we have to retry them because potentially Lambda did pause us for hours and then woke us back up and we were in the middle of flushing data, we have to make sure that that doesn't leave memory. And before the sandbox shuts down, we send everything. So that was kind of the key innovation that we were able to add because we had so much more control over the lifecycle of the function with our Rust-based extension.
Wow, amazing. Like, I'm really, really, really impressed. Hey, is there anything else that you want to add to the story?
No, I think this is great. It's live and open source. You can read it. It's just at the Datadog Lambda extension repo. I'm sure we can put that in the notes somewhere.
Absolutely.
And it was a lot of fun. I think really enjoyable. And now I continue to look for new places we can use Rust at Datadog because I think inevitably in 10 years, everything that we ship to a client will probably be in Rust because it has a lot of good features and good aspects that we like.
Yeah, if we're messing with other people's compute, we want to be respectful of their space.
Yeah, you want to
time.
be as low overhead and as high uptime as you possibly can. And I think there's some good benefits here. Yeah.
Awesome.
So we are experimenting with Rust in many other ways throughout Datadog. We are bringing it into our main agent. There's a project to do that.
Cool.
A lot of our backend where we store metrics data and we store, logs and APM traces is having components of it built in Rust because we get a lot of really, really good performance benefits too. So I'm not the only one doing this. There's a excited group in Datadog that's very pumped about this stuff. Yeah.
That's awesome. Well, I appreciate so much your time and your expertise today. And thank you for sharing this story with us. Goodbye.
Anytime. Bye.